Hey guys, I'm here with Professor Deng. He's a associate professor of one of the most prestigious universities in China, Tsinghua University, and he has a huge background in AI technologies, and he's building his own blockchain project. So, Professor Deng, can you introduce yourself a little bit and your background?
Please call me Steve. That's my English name. I got my PhD degree from Carnegie Mellon University in the United States, and after graduation, I have been working in the Bay Area, California, United States, for almost 4 years. After that, I joined Tsinghua as an associate professor. My research interests in both artificial intelligence and high-performance computing. Basically, we design new algorithms for using the deep learning approach, and we also designing new hardware to improve the efficiency of artificial intelligence computations.
Okay, cool. So artificial intelligence and deep learning and, of course, high-performance computing. So how does that relate to the blockchain?
Actually, I got to know the blockchain probably 2 or 3 years ago, and when I looked into the blockchain technology, I found that there are many challenges hindering the further success of blockchains. The challenges are something like this. First, the latency. The time to confirm a transaction is just too long. It takes probably 30 minutes to confirm a transaction.
On a Bitcoin network, right? Yeah.
The second thing is that smart contract need programming. You have to know how to program before you can use smart contracts. The third thing is the security problem. Actually, the lack of security is already plaguing the whole landscape of digital currencies. Also, the first thing is that mining. Many people believe mining is just a waste of energy.
Right. That's the biggest criticism, because I talk about mining a lot and people show them like these gigantic mines and they secure the network, but they just do a meaningless calculation. They just constantly roll the dice on that. So how did you try to solve this then?
When looking into these problems, I found that artificial intelligence, especially the works has been done in my group, to serve as the key to resolve these problems. So we continue to work on this and develop many different techniques. And now we put these pieces together. It looks like we have a final solution to all these problems. That's why we want to build a new blockchain. The idea is to use artificial intelligence to rebuild the whole foundation of blockchain technologies. So the target is to make it faster, easier to use, and also safer.
So it's completely different. So what attracted me to the project was that you claim that you can go up to 1 million transactions per second and written on chain as well. And you're using AI technology to do so. So how do you want to achieve that? How's your vision to achieve this?
In the current blockchain, the transaction speed is a huge concern. Typically, it takes about 40 minutes to confirm a transaction. The problem is that we do the confirmation over a P2P network. So as long as there are more number of nodes joining this P2P network, so the latency among these, the communication latency among these nodes will have to increase. More nodes, the latency of the confirmation is bound to increase. So in our technology, we use a different approach. The basic idea is to introduce the idea of so-called delegation network. In other words, we do not assign the POW to all the nodes in this P2P network. Instead, we use artificial intelligence techniques to randomly select a small group of nodes. Because we have a much smaller number of nodes in this delegation network, so the latency is significantly reduced.
Okay. When compared to the Bitcoin network. So we've been talking about the Bitcoin network for a long time, and anyone can be a node in the Bitcoin network, which means you end up with basically tens and thousands of nodes all spread across the world. And with countries like China and the Great Firewall, sometimes you do have long latencies and communication issues between the nodes. So what you're saying here is that not all the nodes have the same rights of other nodes, whilst you're using AI technology to allow certain nodes to perform proof of work instead. Is that correct?
Right, exactly. On the other hand, the selection process is totally random, and every node can be chosen as a delegate node in the final smaller network, and the probability of a node being selected is proportional to its POS. proof of stake. Yeah, it's a hybrid POS plus POW approach.
Oh, okay. So it's a different approach in mining. So right now we've seen networks that are faster and they always have a little bit of a compromise. We've seen delegated proof of stake. We've also seen other systems where you delegate your proof over. But in this case, what you're saying is that the chances of someone being selected is exactly the same as their stake, the proportion of their stake, but it's also done randomly using AI. So I guess in a sense that there's less abuse because in the POS system, it's always the same witnesses or the same main delegations that do the selection. But here it's a random selection instead, right? So you're trying to combine that security with the amount of so it's just less nodes, but it's all randomly selected. So that's why how you achieve the faster transaction per second. So if that is the case, then how do you do that selection? Because this problem has been kind of troubling the community for the longest amount of time. It's not very easy to achieve, especially because right now Bitcoin is still the gold standard of doing this because, of course, to make it mathematically certain and prove that this is just as secure as proof of work is really hard. So how do you want to achieve that? And how do you prevent abuse of the network?
We use a random clustering approach. Basically, it's totally distributed algorithm. So every node will vote for its representative. Each node selects some neighbors of itself to be the delegate of himself. Actually, the selection process is based on both proof of stake as well as connectivity. Because some nodes have better connectivity than other nodes inside one network. Giving one specific node, he will vote another node as his representative. Of course, he can also vote for himself.
Okay.
And this method is delivered to its neighboring nodes. And these nodes will exchange information. When a node has more votes as well as better connectivity, he's more likely to win this voting process, to win this selection process. After a certain given number of iterations, we can finally have a consensus which node will win this selection process. Okay. Somehow, it's something like the selection process of the president in the United States.
Okay, so it's all about voting and then channeling the vote. So how long would, if a certain node is voted, how long do they remain, or are they allowed to mine or do proof of work for? What's the duration? How many blocks?
Because you have a P2P network, something like end-to-end delay. You pass one message from one end to the other end of the network. Worst case end-to-end delay. Our selection process will take something like 10 or 15 runs of this kind of end-to-end latency. Not real time, but it's fast.
Okay.
Let me put it this way. Yeah.
So basically it's a little bit like delegated proof of stake, but then it's faster. So now let's talk a little bit about the mining procedure as well. So from what I understand, it's a very different mining procedure than other cryptocurrencies out there. So
actually, we take a dramatically different approach. Our mining function is based on so-called Monte Carlo. It's so-called MCMC algorithm. Basically, this is one of the most important algorithms in the 20th century. Actually, in the statistics, there are two different approaches to the statistics. One is the so-called frequency approach. The other is so-called Bayesian approach. Actually, so in other words, Bayesian approach is another foundation of modern statistics. And inside this Bayesian approach of statistics, one fundamental algorithm is the so-called MCMC algorithm, or Monte Carlo Markov chain. Markov chain. This algorithm is actually it computes the posterior probability distribution. Given some data, you want to figure out which cause leading to this data. So you have to compute the posterior distribution.
Okay.
That's why we use MCMC algorithm. And the MCMC algorithm is a random sampling based algorithm. Basically, you take a sample from something like uniform distribution or Gaussian distribution. Then we use a procedure to reject some samples and accept some samples. Finally, this sample will converge to final distribution.
Okay, so this is
Yes.
really not a hash function per se, because of course with cryptocurrencies we use hash functions, which give a kind of a result you cannot predict when you start mining. Of course, it's really easy to calculate, but of course you have to perform it in order to do it, and it's not a reversible calculation as well. So MCMC, so the hash function that you're talking about is actually not a, is it a cryptographic function, or you said it was a more of a probability statistical function, right?
It's basically it's a statistical. It's a sampling procedure. Let me put it this way: a sampling procedure, and it's a basic computation pattern of modern statistics.
Okay. And why would you want to choose this? Why do you want to replace the hash function? Because this is something that really caught my eye, because I think it hasn't been done before in any other blockchain. We talked about other hash functions, but they're all hash functions, right? So this is more of a different computation. So why do you want to do this, and what's the advantage of doing this?
Actually, hash function is good. It has many desirable properties. But the only thing that when you use hash function, you do the mining. The mining itself is meaningless for outside the world of cryptocurrency. So, but on the other hand, MCMC is a very useful computation patterns for any almost any statistical computations. So, if we can use MCMC as a mining function, we can use the mining to do useful things for big data analytics. That's why we want MCMC. And at the same time, MCMC has many desirable properties to work as a mining function. First, it's time consuming. It needs a lot of computations before you can converge. The second thing is that you cannot predict the results before you do the MCMC computation, because you are taking samples to converge to a target distribution. At the initial stage, you do not know what samples you would have after computation. The third thing that, although it's very difficult to compute, but it's relatively easy to evaluate how close you are from the convergence. So, given some samples, you can check how close you are to the final convergence results. So, these three properties make it a good choice for mining functions. At the same time, if you do the mining using MCMC, we can unleash the power of miners for big data applications.
Right. See, this is the biggest problem and the biggest objection to mining, because the more people that join a mining, especially if it's Bitcoin or other proof of work systems, it makes the network more fortified, but the calculation itself is just doing it again. It's just rolling the dice again and again, and it's not producing any results. It's not improving science or doing anything in any way. So this is the interesting thing about matrix chain, which is they're not using a hash function per se, but they're using a calculation that's used in statistics and scientific and probability calculations. So by doing mining, you're actually doing kind of calculations that can be used. And so do you feel people will outsource calculations to you guys? They'll be generating a very big mega computer for AI. Is that kind of what you're doing here?
Yes, yeah, that's our target. Actually, we will design business models so that on the one hand, we can accept different computation jobs from customers, no matter it's in the big data domain or in the scientific domain. Then we somehow allocated the jobs to different miners. So each miner will do some MCMC computation and finish the job they are allocated. Then
that's the crazy part. So the more computers that are part of the network, the more powerful the computer is. The objective isn't, of course, to just secure the network, but you can actually do work. You can actually put that calculation into use. So now instead of just burning energy for rolling a dice, you can do scientific calculations, and you can work your business model around getting projects onto this system. So one key property that you talked about, and that's essential for this, is that there's no predictive result, right? So essentially, if there is predicted results, the miners will pick work that would probably lead to block creation better. But so we saw some things like ASIC boost as well. So ASIC boost, you looked for collisions and try to improve mining efficiency. Is something like this vulnerable to something like this, where miners will be more selective, or is there any vulnerabilities to having MCMC instead of, say, a SHA-256 having chain algorithm?
Actually, MCMC somehow it involves a lot of random sampling. So current computers do not do a good job for this kind of stuff. You can do it on computer, on GPU. It's doable, but the efficiency is not very high. It's not satisfying. So in our approach, actually we already have a prototyping Bayesian computer, so-called Bayesian computer. We designed a new kind of hardware. Basically, we can direct support the randomly sampling process as well as the statistical computations. So our target new type of mining hardware, which we call Bayesian computers. Currently, we already have a prototype. Actually, our GitHub repertoire, we already have the source code released.
Okay, so it's the source code for the Bayesian computer. But in terms of hardware, is it built yet, or are you going to sell that as a miner in the future?
It's in Verilog code, and you can synthesize the code and make it available on FPGA.
Cool. Cool. So now when you're mining, you're actually doing scientific calculations. So it's a different business model, but you're actually helping science, and that energy is not wasted. So I think that's the kind of interesting part about this. It's not just about low efficiency, but you're completely using mining to solve scientific problems. I think that's what kind of attracted me to this. So the last aspect of Matrix blockchain is that you're using AI for smart contracts. So how are you using AI for smart contracts? Because I've heard AI is huge these few years, but how does that help with smart contracts?
Actually, recently, many people, like many researchers in Microsoft and Google, they're using deep learning to do the code generation. So it's something like you give a description of your program you want to build. You can describe the intention of the programming with something like a template or script language, something like that. Then a deep neural network will automatically convert this intention or this script or this template into an executable program. So we're using the same approach. We will define something like a template. The template can be something like natural language or just something or some written language with a special format. You use this template. You define the transaction conditions and results and actions. Then from this template, we use deep neural networks to generate a program for the smart contracts, something like that.
Okay, so essentially I can basically say, hey Siri, make me a smart contract. If someone gives me 10 man tokens, I can give them a cat or something. You know, is that something that is
something like that. Yeah.
All right, but one thing that happens is this actually realistic? So, you know, I've tried to learn coding, and I realized that when you're coding, you're starting to think in terms of a computer. But is it realistically possible for these contracts to be made by either just writing something down, a lame person writing something down that's not done programming? Is that achievable? Has that been proven to be successful right now with current technologies?
Yeah, that's a very good question, actually. For general programming, it's a still very challenging program. I would say not every program can be created in this way, but for smart contracts, we have something. It's somehow easier because for smart contracts we have a limited set of program patterns. According to our research, we found that there are only like 40 to 60 program patterns inside smart contracts. Yeah, so we can use deep neural network to identify the intention for the smart contracts. So you somehow this contract will belong to a given set of computer patterns, and meanwhile we can use another neural network to automatically convert the template into a program, capturing the computer patterns.
Okay. Then let's say hypothetically that is the case. So I have a swap contract that I wanted to make. So the swap of tokens for a digital cat. So in this case, how do I verify that this is true? So I just told this program, I want to build a smart contract. Someone sends me 10 man tokens and I give them a cat. How can I verify? Because now that I said that, I'm paranoid that maybe the contract is wrong. Maybe my intent is incorrect. Is there any way for me to verify that?
Yeah. Actually, we have something, there's another line of technology in our project. Basically, we also use AI and the formal verification techniques to verify the security of your smart contract. So this formal verification tools and deep learning tools are built inside the client for every user of our blockchain. So after they create the program, we have tools to automatically check the security of this program. We can do either a static check to identify the loopholes inside the program, and we can also simulate the execution of your smart contract to identify the dynamic bugs. Of course, we cannot cover all possible bugs, but but we can cover most bugs available so far. Yeah.
Right. So you're basically trying to use AI technology to not only make sure that I get it done, but it's also try to make it as bug-free as possible.
Yes, exactly. Yeah.
Okay. Because right now, smart contract bugs are probably the biggest issue plaguing the cryptocurrency community right now. A lot of contracts are written very quickly, but as a result, they might have fatal flaws or logic issues in them. So the idea, of course, is, I guess, because you identified there's a small pool of smart contract archetypes or styles, then you can just converge into those and something that's already made before. So instead of having infinite number of things that a program can do, you only have a few small ones. So that means it's going to be easier to do it. So how close are you to actually delivering on such a project like this? So it sounds like it's got these ambitious goals. It's totally next generation AI. This whole artificial intelligence. It's super smart by itself. Then how close are we to achieving this?
Actually, we'll have a working blockchain by the end of September.
Okay.
And inside that, in that release, we'll have the fast we'll support the fast transaction. We just talked about earlier.
Okay.
And end of this year,
okay,
we'll have the second release of our blockchain, which will include the technology for smart contract generation as well as enhancement techniques.
Okay, so by the end of this year, that's quite a fast deadline to complete it. So do you have a kind of a testing version of your blockchain right now? Is there a testnet up for this kind of proof of kind of hybrid network system?
We have tested version. It's already operating in my lab.
Okay, in your lab. Oh, cool. So now, a few questions about security. So right now, because you're promising such a fast network, of course, the problem that, of course, blockchain solved is the Byzantine general's problem. If someone sends, someone in the network wants to be malicious and wants to attack the network. So have you done any tests to ensure that this some potential attacks on this network won't happen, or have you dealt or tried to prove that the system works? Like, what sort of proofs have you done?
Currently, we have a simulator. We have basically a set of computers, and we run a network simulation to demonstrate our ideas. And in the future, we'll build a real network. It's still a network in our lab, but we'll use that to simulate different attacks. And we already have a library of known attacks for smart contracts. So we're using it to do experiments of our techniques. So in the future, we'll have a larger pool of simulation nodes.
Okay. And another question that's just out of interest, because we're not using a hash function, so we're actually doing a calculation. So will the users of the network benefit from the potential business development you can do by using this network and selling that computational power?
Yeah, it's quite doable. It's quite doable. Actually, the Bayesian computation is a very important direction in machine learning. Currently, many people are talking about integrate both Bayesian computation and deep learning into a more powerful tool of artificial intelligence. It's called Bayesian deep learning. So it's very useful for many different things. For instance, we can do the gene regulatory network computation. Basically, we simulate the whole genome of a human person. And we can capture this as a Bayesian network. Then we can simulate the interaction between this network and some kind of a new medicine.
Right.
It's a very complicated process, but we can do that. We can use something like a customized medicine for every people. It's very useful. And And the Bayesian computation is also has an application in many different domains, such as video analytics, such as financial modeling, such as chemical reaction simulation, and many others. So,
right. So if you do that, if you use this, because you're kind of building this biggest supercomputer for Bayesian calculations, right? So you have, instead of mining, you're using this whole network to solve Bayesian problems. But the thing is, do the miners get paid for that as well? Because right now miners get paid for securing the network, so they get paid by the network for stuff. But if for example, if you rent this supercomputer out to a university or a financial institution for them to do calculations, they'll probably pay you money, right? They'll pay you maybe fiat dollars or something like that, which would be giving that back to the community.
The reward for the miners would include something like something like our token, and something like the reward for computation itself, something like the gas in Ethereum.
Okay, so you may be rewarding something for gas, and it depends on who's using the network and who's using kind of the supercomputer at this time, basically. So it's a decentralized supercomputer that does the Bayesian function, and of course, it also does mining as well. So it's two in one. That's why you're not wasting energy, basically, on this thing. Cool. That sounds great. So thank you so much, Dr. Deng, for coming over and talking about the Matrix projects. I think learned a lot about how to do a different blockchain, and I think it's and very interesting project to learn, because I think this has never ever been done before, and I wish you the best of luck with the Matrix project.
Thank you. It's my pleasure.
Awesome. Thank you.